Chalo bachcho, welcome to today's class. We're starting a really interesting topic from Unit 8, the electromagnetic spectrum. Now, I know it sounds a bit heavy, but it's super important for your exams. So, tension nahi lena, we're going to make it so simple, you'll understand it and remember it for life.
Okay, let's dive right in. To get our brains warmed up, I want to start with a very simple, but maybe surprising, question.
Just think about this for a second. The light that's coming from a bulb in your room and the signal that your radio is picking up from some far-off station, could they actually be the same thing? Fundamentally the same? It seems a bit strange, doesn't it?
Well, the surprising answer is a big yes. They are absolutely the same thing. And the secret to understanding this, the connection, lies in knowing what an electromagnetic wave, or an EM wave, really is. Let me give you a simple analogy. Imagine you're at a cricket match and the whole crowd starts doing the wave. Now, what's actually traveling around the stadium? Are the people running around? No, of course not. The people just stand up and sit down in their seats. It's the pattern, the disturbance, that moves. An electromagnetic wave is exactly like that. It's a disturbance that travels through space, not some physical object.
So how does this disturbance even start? Well, it's like a beautiful dance between two partners. The electric field, which we call E, and the magnetic field, B. You see, they're linked forever. A changing electric field gives birth to a magnetic field, and in return, that changing magnetic field creates a new electric field. It's this continuous back-and-forth cycle of creation.
And here's what you get as a result of that dance. It's a self-sustaining wave that just keeps on going. Look at the diagram. The electric field is oscillating up and down along the x-axis, and the magnetic field is going in and out along the y-axis. Notice how they are perfectly perpendicular to each other? And the wave itself, it moves forward along the z-axis, perpendicular to both of them. So the really crucial question is, where do these waves come from? What kicks off this whole process? The answer is so simple. Any accelerating electric charge. A charge that's just sitting still won't do it. A charge moving at a steady speed won't do it either. It has to be accelerating, or you could say oscillating back and forth. That's what radiates these amazing electromagnetic waves. All right, now that we know what an EM wave is, let's see how this one simple idea builds up into a huge, vast, and mostly invisible rainbow of different waves. This is where it gets really cool.
First things first, let's get the official NCERT definition, which is super important for your exams. The electromagnetic spectrum is nothing but the classification of all these waves according to their frequency. That's it. It's just a way of organizing a huge family into different groups based on one simple property.
And this entire family, the whole spectrum, is governed by one single beautiful relationship. I call it the magic formula. C equals F times lambda. Here, c is the speed of light, which is a constant in a vacuum. F is the frequency, and lambda is the wavelength. And this tells us something very important. As the frequency goes up, the wavelength has to go down, because their product always has to equal c. They're inversely proportional. Now this slide here, this shows you the whole family in one picture. On the far left, you've got these long, lazy radio waves with a really low frequency. And as we move across to the right, you can see the frequency keeps increasing and the wavelength keeps shrinking, all the way to the other end, where we have these tiny, incredibly high-energy gamma rays. So let's take a quick tour through the main members of this family. And just remember one simple rule. As you move from left to right on this chart, from radio to gamma, the energy of the waves gets higher and higher.
Okay, so first up we have radio waves. They bring us our music and TV shows. Next are microwaves, which cook our food and are used in radar. Then comes infrared, which we feel as heat. It's also what your TV remote uses. And then look at this tiny, tiny little slice called visible light. That's the only part our eyes can actually see. Right after that, we have ultraviolet or UV from the sun. That's what can give you a tan. Then come the powerful X-rays that doctors use. And finally, the most energetic of them all, gamma rays, which come from nuclear reactions. Remember, they are all just EM waves, only their frequency is different.
Okay, the theory part is good, but let's actually apply our magic formula to a typical question you might see in your exam. This will really make sure we've got it. So here's the problem, a very common type. An FM radio station is broadcasting at a frequency of 100 megahertz. Your job is to find its wavelength. So what's our first step? We start with our magic formula, C equals F lambda. The question wants the wavelength, which is lambda, so we just need to rearrange the formula a little bit. Wavelength equals the speed of light divided by the frequency. Simple as that. Okay, now we just plug in the numbers. For c, the speed of light, we'll use 3 into 10 to the power of 8 meters per second. For f, the frequency, it's 100 megahertz. Now be careful here. Mega means 10 to the power of 6. So 100 megahertz is actually 100 times 10 to the power of 6, which is 10 to the power of 8 hertz. So our calculation becomes 3 into 10 to the power of 8 on top, divided by 10 to the power of 8 at the bottom. The 10 to the power of 8s just cancel out, and we're left with just 3. The wavelength is 3 meters. Can you believe it? The radio waves from that station are literally 3 meters long. Samajh mein aaya? See? It's really that simple when you break it down.
All right, now for a very important section. Let's talk about some silent killers. These are the common mistakes and wrong ideas that many students have, which can cost you marks in the exam. Let's clear up that fog right now. The biggest confusion by far is thinking that these waves are like sound waves. Sound needs air or water or something to travel through. It needs a medium. But electromagnetic waves are totally different. They don't need any medium at all. They are disturbances in the electric and magnetic fields themselves, and those fields exist everywhere, even in empty space. In fact, EM waves travel fastest in a perfect vacuum. And please remember this second point. So many students think that light and radio waves and X-rays are completely different things. They are not. They are all members of the exact same EM wave family. The only thing that's different is their frequency and their wavelength. That visible light we see, it's just a tiny, tiny sliver of that giant EM rainbow that our eyes just happen to be able to detect. Okay, let's zoom out for the grand view. It's time to connect this topic to your whole syllabus and then summarize the absolute key takeaways for your exam. You see, this chapter is so important because it's like a bridge. It takes everything you learned before about electricity and magnetism, and it connects it to everything you're going to learn next in optics. It shows you that these aren't separate topics. They are all part of one single, beautiful story in physics. So if you remember nothing else from today, just remember these 5 exam-safe points. 1, it's accelerating charges that produce EM waves. 2, the E and B fields are perpendicular to each other and to the direction the wave is traveling. 3, all EM waves travel at the same speed, c, in a vacuum. 4, the master formula is c equals f lambda. And 5, the spectrum is just a family of waves from radio to gamma, arranged by frequency. And to end, here's a little something to think about. We see the world in visible light, but what if our eyes could see microwaves? What would your Wi-Fi signal look like floating in the air? What would a running microwave oven look like? It really makes you wonder, what other invisible realities are all around us, right now, just waiting for the right kind of detector to be seen? Something to think about.